So in this hour, or a little bit less, I will try to show to you the results of a study that is mainly focused on the optimization technique. So this is mostly related to the technique rather than the problem. The problem we have already examined. It is the local energy community, but the idea can be applied also to different problems. And the technique is the distributed optimization. So until now we have seen a unique optimization problem for all the community in this case. So the optimization of the community with a central optimization. And the optimization is carried out by taking the measurements, the data that are available by the monitoring systems of the users, collects all the data, the present data, and also the forecast. Also collect all the technical parameters of the installations of the device, of the generators and loads inside each user. And then with the optimization, so an objective function, obtain the results and deliver the scheduling of storage or distributed generation to the users. This activity means that all the data of the users need to be shared with the owner of the energy community. So there is a privacy issue there because some of the users, they don't want to share all the data and also the forecast or their consumption or all the device. There is also a concern about the capability to collect all the data by the energy, the manager of the energy community. And so there is a good reason not to try to implement something different, something that is distributed the goal to optimize to all the users. So the users, they are carrying out an autonomous optimization, sharing just the data that are needed in order to obtain the common result, so common coordination. So sharing just the data that are needed for the coordination of the optimization problems that are solved by the several users. So I will take for this purpose, this comparison, the example of a low voltage, in this time low voltage distribution network with the several users in the low voltage distribution. And for this I will focus on the dead scheduling, but also I will try to show also the results of an activity for a procedure that is intraday, take into account also the uncertainty, so several levels. I will start here just to say what are the different aspects of energy community. The first is planning, so establish the thing that the installation of energy community may also have an effect on the grid investments, because if the energy communities are able to balance load and local generation, probably also the expected improvement of the network can be reduced. And scheduling, the intraday scheduling control, also the settings of the price. And the last one is the service of the network. In this hour, I will focus on the scheduling, the add, and also in the settling of the prices and network charges. So this is the example. So there are two feeders with with some users, and it is a low voltage distribution network. We can write for this network, as we have done also at the beginning of the morning in the first lecture, a centralized optimization for all. So we have here the usual objective function, and it is the summation for all the users. So this is an optimization for all the community that takes into account all the users. Here the symbols are quite similar as before. There is this sell buy grid and sell grid. It means consumption or injection to the retailer, and these are the what we mentioned before, PLEC, the transaction, the internal transaction. We wanted to be more specific because we needed to distribute it. So we want to know exactly what is the transaction. So what is the seller and what is the buyer. So we are specifying here I and J, I and J, I and J. So for each transaction, peer-to-peer transaction, there is one that is selling, so injecting power, and one is buying, so is buying power. Obviously, the amount of power or the amount of energy for a time slot, needs to be the same. No? So as much as you sell, the other needs to buy the same. So this is our constraint. So you said before that was a global, this is specific of IJ. There are also other constraints for power balance, avoid simultaneous purchase and selling by the same prosumers, and model of the battery energy storage. I will go into the details, but before that I would like to show to you, these are the cost revenues. I would like to show to you the version that is distributed. So this is the distributed version in which the objective function is for each user case. So each user has his own objective function. You see that it is more, it is augmented with respect to the objective function of in the centralized optimization. Of course, the user tries to minimize the power or the cost associated to the absorption or consumption of power from the reseller, and there is a minus, so increase the power that is injected, so takes into account the revenues. But then there is a plus with these two terms. What are these two terms? Is that the user cannot interact only with the reseller, but also can sell or buy electricity from other prosumers of the community. So in its optimization, in the optimization of the single user, we also include these that obviously cannot be included in the optimization of the global community, because these are compensated, because as much as power is injected into the network, as much is sold in the other. But for the single user, these are not compensated, because they or buys or sells for each time. So we add the summation for all the transaction that that prosumer K can have with another prosumer J. And obviously he can buy from prosumer 1, prosumer 2, prosumer 3. So this is the idea of this summation. And this is also for the power that is injected. So the prosumer, if he has a generator that is larger than the local consumption, inject to the network and directly transact, so sells power to some of other prosumers. And this is the summation. You see that we need to put in this lambda. And these lambda are the prices of these internal transactions. But these prices are different from the prices of the transactions with the resellers with the grid, because the prices with the resellers are fixed, are predefined by the resellers with the contract. These lambda are automatically calculated by the distributed optimization. So the distributed optimization needs to calculate these lambda that are the prices of the internal transaction. Which is the idea behind this calculation of lambda is that it is better to go to this. We need to say that for each transaction, the amount that is sold by prosumer I should be equal to the amount bought by prosumer J. So there is this equivalence. So if you have that there is a disbalance. So if you have that the price of selling by a prosumer is quite high, it tends to export power more. If the price of a buyer is low, it tends to consume more. In order to get a balance, if you have more power that is sold than that one that is bought, automatically the distributed optimization tends to reduce the price of the selling, so tends to reduce the incentives to sell the power, and increase, if there is, and decrease the price of who is buying. So he is incentivized to buying more. So it is here. So the idea is that this distributed optimization is an iterative procedure. It is not a single step, just a calculation, but there are interaction. And what is exchanged between the prosumers are the lambda. So the lambda values are the coordinating variables that coordinates the production and the consumption of the various producers and the internal transactions. So since these lambda are called Lagrangian multipliers, the method is alternating direction method of multipliers or ADMM. These methods, it is iteratively, so we start with some values of lambda, and then the lambda at each iteration are adjusted. I will show to you also the scheme, the detailed scheme for this adjustment. But you can understand that this procedure might involve many iterations, so there is a convergence issue before reaching the final results, that is the results where these constraints, I do apologize, these constraints are met. So we need to obtain a solution in which there is this constraint, this balance is obtained. So in this, in order to speed up this optimization, in general we add also a term that facilitate the convergence, because it is a penalization of the missing balance. You see that this term, it is the difference between buy and sell for each users, in which you have this hat that is the results of the previous iteration. So at each iteration, this takes into account the mismatch, and the greater the mismatch, and this is penalized by this coefficient here. So at the end, we obtain the results in which, since it is a minimization, this L will be 0. You see that it is squared, so it is not affected by the sign, so it is not positive, negative, it is always positive, and we tend to decrease, so we tend to penalize the deviations with respect to the previous iteration, so the solution achieve the results in lower number of iterations. Any questions so far? So we can see also, yeah.
How to decide this penalty factor? Based on this is trial and error method, or?
Yes, I will show you that we start with a value, and this row is updated at each iteration in order to take into account the mismatch, so in order to reduce the mismatch. So if this mismatch is low, I mean, we can increase this row during the thing. But there are tricks, several tricks. We have implemented this, obtaining good results, but for the various problems, there are also tricks in here. So I would like just to recall also the other constraints, and in particular we have the no simultaneous purchase and selling. It is quite strange that a prosumer can sell and buy in the same time, but from the mathematical point of view, since they are different variables, can happen. So we need to force that there is no this behavior. So we are introducing this binary variable u for each producer, so for each user, so or he can buy or can sell. Obviously the same sign with the grid and the transaction needs to be met, and each user has a capability, so these are positive quantities, but there is a maximum value of the power that can be sold or bought by the characteristic of the user. And there is a battery storage that are important in this activity. The storage is fundamental there. So we have the usual simple equations that says that the energy is the level of the energy in each battery. It is the energy in the previous period plus the power in the period, and the power is always multiplied by the efficiency or divided by efficiency if it is charge and discharge. So you can see that also here we have introduced the binary variables in order to avoid that the battery is charged and discharged at the same time, because we use two different variables. So having two different variables, so then in the mathematical problem you can also obtain the solution with charge and discharge not zero, both not zero at the same time. That is not reasonable. Obviously also the battery has the maximum, and there is a maximum minimum level of the energy inside the battery. I don't know, 20%, 100% or 90%, no, the maximum of the size of the battery. Power balance, here we have a thing. We don't want to introduce all exactly the equation, the power flow equation and so on of the distribution network, because it is low voltage and it makes the solution a little bit complicated. So we have preferred to implement the method, and we succeed also to implement the method, by just taking into account the losses into the network. So you see that here in the power balance, we have data at each time. There is the generation, the discharge of the battery, the power that is absorbed by the grid, the power that is bought by the other prosumers, plus, and you see that there is the demand, the battery that is charged, the power that is sold to the grid, the power that is sold to the other prosumers, and then we take into account also the losses inside this transaction with this term. That is a simplifying way, and we have adopted this kind of trick, we can say. We do this in two stages. So in the first stage, these losses are just, these are the resistance of the branches, of the low voltage branches in the feeder, and these losses are the square of the active power flux into these feeders, into the branches. Take into account the voltage and so on. And the flows are just given by this simple constraints that takes into account the topology of the grid, so where the users are connected into the network by using these matrices A grid plus, and these matrices here that takes into account the topology and the connection of the various users into the feeders. So, for the second stage, a refined calculation, we can take into account the calculation of the first stage, and the calculation of the first stage gives a sort of efficiency of each transaction. So we can associate to each transaction, to the grid, and to other prosumers, some kind of losses. The losses divided by the power that is transmitted and so on gives an efficiency of this transaction. So we can repeat the same calculation by including, instead of these losses here as before, these coefficients, this efficiency calculated by the first stages directly. So we can say that when we buy electricity, we buy a little bit less, no? Because there are the losses into the network. And when we sold electricity and so on, we needed to sell more, a little bit more, because there are the losses in the transaction. So in this way, we can also include, if you wish, the losses in the transaction. The idea behind this was that this particular community, low voltage community and so on, may be also the owner of the network. So he is interested on lowering the losses into the, let's say, internal network of the community. Okay? In the scenario of this morning, there was the distribution system operator, so it will be the case of the distribution system operator to deal with the losses. Any questions so far? So this is the idea. So this is the, a little bit, I do apologize that is not visible. Well, it is not completed. It will be completed during. I will try to describe the procedure that is not so difficult. It is a little bit tricky to obtain a convergence in a reasonable time. No? But the idea is that we start at the beginning with the initialization of the lambda, that are these multipliers that needs to be that coordinates the single optimization of the various users. And then obviously we have the optimization model, and we obtain a solution that is not meeting the requirements that the power that is sold is equal to the power that is bought. There is someone that is selling too much or too low with respect to the other part that is autonomously optimize the thing and say, okay, I want to buy a lot from that guy, but The other optimization that is independent, carried out independently, says, no, I don't want to buy, to sell. No? So there are at the initial. So at this point, the lambda needs to be updated. It is a second iteration. So how to update this lambda? We calculate the error. So there is a coordination part, so the results of the single optimization are given by the central coordinator, and the central coordinator calculates the error between the power that is bought and the power that is sold by in each transaction, and says, okay, there is a mismatch. This mismatch is R, this R. So he wants to update the lambda so that R will be reduced in the next optimization. So it will increase the price if one user is buying too much. It will be decrease the price if the user is buying too low. No? And for this this reason, also the selling will be coordinated. And this, you see here, there is the equation that we have implemented in order to update this lambda. The lambda at the further iteration, and the iteration is indicated here, there with a ni plus 1. Ni plus 1, it is the iteration. It is the lambda of the previous iteration plus something that multiplies this error. So the larger the error, the larger is the deviation of lambda. If the error is positive, it means that we are selling, we are buying, this is buying too much with respect to what is sold, so we need to increase the price. If this error is negative, it means that what is bought, it is lower than what it is sold, so we need to decrease the price. It's good until now? Then there is the trick for rho that is not fixed because we want to decrease the number of iterations. So this rho, it is updated at each iteration or some iteration. On the basis of both the error, so the mismatch, that is called the prime residual in the literature, but also with the deviation with respect to the values of the previous iteration. So we don't want to obtain the behavior in which all the quantities in each iteration goes up, down, goes up and down. So the variation with respect to the previous iteration is penalized. So penalized with respect by using this rho. So rho increases or decreases, take into account also this so-called, in the literature they say, dual residual, that you see that there is the ni minus 1, it means this iteration and the same results of the previous iteration. So this is the idea. So we tend to adjust rho in order to minimize also the deviation with the decisions of the previous iteration, in order not to have some kind. When this procedure stops, when this residual, primary residual, so the mismatch for each transaction, so this is specific for each transaction ij, it is lower than a tolerance. So if it is greater than the tolerance, we need to iterate. When it is lower than the tolerance, it means that I don't know if I can be back to be clear. it means that this constraints for each transaction is lower than few watts. We put a limit of 5 watts and something, and so we say, okay, this is the solution. Okay, the results are the branch power flows, the energy transaction, the prices of the transaction, and the battery energy storage. And I mentioned this morning that the price of the transaction can also be obtained by the shadow price of these constraints in the centralized optimization. One of the results that we like in this study that we have obtained, that if we implement the centralized optimization and the decentralized optimization, although these prices are calculated in a completely different way, in the centralized optimization are given by the dual variables of the constraints. In the distributed optimization are these parameters that are updated at each iteration. At the end, the results are the same. That is a good thing for the idea, no? The test case, 1 day divided by 96 periods of 15 minutes each, low voltage feeders. Each feeder consists of 5 lines. There are 5 prosumers for each feeder, and the total day consumption it is mentioned here with a production, PV production. We consider 73 production. We consider also a best unit for each unit, so for each prosumer. So we can increase the complexity of the work. These are the profiles for the load and PV production. This one. This is the price of the resellers that we have considered. These are just the data for the area of the PV panel for each of the 10 users and the size of the batteries. It is limited because they are low voltage users, and these are the comparison between the results of the distributed optimization and centralized optimization, practically the same, without batteries, and this is with the batteries. Obviously, with batteries is a little bit more difficult, no, with all the batteries to obtain the convergence, but you see that the results are quite similar. And also this is the energy in the battery energy storage, and the total with the decentralized, the IDMM. You see that both the decentralized and distributed, they use the storage more or less in the same way. These are the objective function with the cost, so you see that are very similar, and also for the losses. These are the prices that are calculated. They are practically the same with the distributed optimization, the centralized optimization. So I will describe just these cases. This is without BESS. And what is shown in this figure, or try to be shown, because here it probably, if you can see there, is better. The blue line, the solid line, it is profiles of the price of the reseller when you buy electricity. We have assumed that the price that is recognized when you inject to the reseller, to the grid, power by the reseller, it is lower, it is half. It is the half value of, it is the red curve. And the dots are the prices of the transactions in each period between the members that are transacting that period. Okay? So that is the dots. Obviously, in many periods, there are no transactions, so there are no price. One thing that we have seen, and this is a little bit a good thing from the theoretical point of view is that although in the same period, so you may have several transactions between 1 and 3, 1 and 5, and so on, the price is calculated by the two methods for all the transactions in the same periods are the same. So there is a single dot for each period, not a multiple dots, because the dots are coinciding. And this is a good thing, because it is strange that in the same community, two members transact in a price and other members transact a different price. If there are no congestions into the network, it is strange to see different price for different transactions. And indeed, the two methods shown that. Another thing that these dots are showing is that these dots are not different from the prices of the resellers. They are aligned to the blue curve and the red curve. In some periods to the blue and to the periods to the red. Never in the middle, no? All the two. When they are aligned to the blue, we have compared this figure with the previous figures of the transaction, the global transaction with the grid, the power to the grid. The power to the grid that I shown you before. Exchange with the grid. So you see that in some periods, globally, the local energy community, the community, this part, it absorbs power. It absorbs power from the grid. Then there are other periods in which it is negative, so it means that it injects power to the grid because there are a lot of photovoltaics, the load is low. And then there is a period at the end of the day in which again the community absorbs power from the grid. You remember probably the load profiles. You see that the load profiles are quite high at the end of the day and low in the middle, but in the middle you have the photovoltaic production, so that makes sense. So take into account this here. If we are going here, you see that the price of the internal transaction are aligned with the price P buy, so when you buy electricity, when globally all the community takes power from the grid. They are aligned to the red curve, so to the price that is recognized when you inject power to the grid, in that period. So globally, the price of the internal transaction tends to alienate to the pi buy when globally the community buys power to the grid. And the idea is that, in those periods, the internal production is lower than the internal consumption. So the people that are selling power, internal transaction, I'm thinking some humanized of this behavior, say, okay, I'm selling to you at which price? Or if you don't buy to me, you need to buy to the grid. So the grid gives this price, so I give you this price. I don't know, minus an epsilon, but you are. So this is the reason why globally, when the community buys power from the grid, the price of the internal transaction tends to alienate to the power that is. Another story when there is overproduction. When there is much production and no load, the grid, this community sells power to the network, and the retailer, we say, at this point recognize this at a pi sell, so at the red value. So the people in the community, I'm trying to humanize this, say, okay, if I'm not selling to me, I need to buy. If you don't sell to me, I know for sure that you need to sell to the retailer, and the retailer gives you pi cell. Why I need to give you more? So this is the price that is alienated with the red curve. So it makes also sense, no? To this, no? The results can be explained, otherwise it is. When there are batteries, you see that the behavior is almost the same, but you see that there are small deviations, no? And this is due to the fact that the battery, when it is charged in one period and it is discharged in another period. So the energy that is put in the battery has been charged when the price was different from the price when the battery is discharged. So this a little bit modifies, but a little bit, not much, modifies the behavior, and these dots deviates a little bit with, from the previous behavior. Make sense? Do you have any question? So this was the results. I can also show to you the tables with the results. Still also with here we have in this table shown the procurement cost, energy procurement cost, negative values indicated the revenues for each of the prosumers. So 10 prosumers, centralized ADMM. So distributed optimization gives practically the same results, and you see that there are some prosumers that have a minus and plus because they are selling or buy electricity, and this is without internal exchanges, and you see that the costs are for all that have positive costs, they are higher, and for those that are negative costs, they are, I mean, in absolute terms, lower. So all the users, they have a benefit or not a damage from the participation into the community, although they have the different panels, different storage, and so on, different characteristics. This is the same idea with the batteries. This was without batteries, this is the battery. We have also analyzed the scalability of this method, so not only 10, but also in a single feeder or in double feeder like this. And okay, the same data before. The convergence of the method can be described in this way. It is okay. These are the number of iterations, and you see that this is the error. So these blue dots are the error, the residuals. So when the iterations increase, and by increase the number of iterations, this residual goes down, down, down. When it reaches this very low value, this is the mean value of the residuals in this axis. When it is low, we can say that we have reached the solution. You see also the behavior of the objective function and also the augmented objective function. The objective function is without L, the augmented objective function. So you see that it starts from here or here. The objective function increases and then it is stable. So you see that even though the residuals keep some additional iterations, so the method tends to converge very, very early, and then there are no much deviations, at least in the objective function. You see this behavior without BESS, and with the battery energy storage, you see that the number of iteration is increasing because it is makes more flexible the operation of the system. Then it is more difficult for the algorithm to find the solution because it has more possibility to find. This is we say that the iteration is 46 iteration for battery energy storage units. So the solution time for us, we count it is 300 seconds, but there is a trick here, that we do the optimization, the single optimization in series, so 1, 2, 3, 4 following. But we can also do in parallel and then decrease a lot, because we don't need to do all the optimization one after the other, but they can, since they are independent, they are distributed, they can be done in parallel. So this is the thing. This is for configuration B, so all the uses in the same feeder and the same idea, and then the configuration C for 2 feeders, very long. So it is, we can see that there is also an advantage from the algorithmic point of view. So if you increase a lot the number of users, the centralized optimization has some difficulties. After 1 hour and a half, the problem was not solved by the we use Cplex, so the Cplex algorithm cannot find the solution. Gives the gap is too much. The distributed optimization reaches a solution. So the distributed optimization, when the number of users is very big, can be also a way in order to address the issue of the dimension of the problem. That if the problem is too large, by discretizing, separating the optimization can be useful. But that was not the primary purpose. Was in general it is the privacy issues that we mentioned. I would like to devote just, I don't know if it is possible, few minutes also to show to you a scheme in which we try to take into account also the uncertainty of the forecast, because we do this optimization the day ahead, but the day before we can know a little bit the forecast of the photovoltaic production, also the load, during the day, but not very precisely. So we can try to include the uncertainty. So we have applied this method that is quite traditional, so there are nothing very new, that is trying to use this multi-stage stochastic scheduling. So the idea of multi-stage stochastic is that from the forecast of the day ahead, we create several scenarios. So we say, okay, there is an uncertainty. So from one profile, we can say we can obtain other 60 profiles. So several profiles, and both for the production and for the load. And then we can obtain then a tree of decisions for each stage. What is the idea of the stage? Is that we calculated the optimization in the previous day, but thinking that during the day the uncertainty increases, so we can update our decisions during the day. So instead of taking just one decision at the beginning, we say, okay, for example, 4 stages here, in other 3 points during the day, we can update our decisions, take into account the actual condition into the network. So in the day ahead, we have obtained this scenario-based solution, this tree of solution that I will show you after, and then we can also implement a rolling horizon optimization during the day. So at each stage, we can conduct an optimization for that stage, and take into account the results of the previous optimization, and take into account that in our case, the level of the batteries at the end of the stage needs to be the same as the one calculated in the previous day in order to take into account all the optimization of the day, not only for that stage. So in order to have a link between the decisions of the day ahead and decision during the day. I will try to give some details of this. And these are the creation of the scenarios. We start with this profile of the photovoltaic, the head, and we create several scenarios around this behavior. And also for the loads, we have several different scenarios with some uncertainty, some level of uncertainty. And then this is the description of the multi-stage. We take into account this parameter, we can say the value that is now stochastic, because it is affected by the uncertainty. It is the difference between the photovoltaic production for its users and the load for its user. And the idea is to create this tree of decisions. So for sure, at the beginning of the day, we have just a single scenario because we don't know the future, so we can calculate. And then after, in all these stages, so you see that we have 3 scenarios. Why 3? You said 60, no? Why? Because we have grouped the scenarios similar by using the k-means procedure. If you have many scenarios, the stochastic optimization is, blocked because it's too much the effort. So instead of considering in each scenario, in each stage, consider all the scenarios, we say, okay, we take, we calculate 3 scenarios that are representative of all the population. And these are the means. So the k-means method, it means that we calculate 3 behavior, 3 profiles that are representative of all the population, and they are minimizing the distance, the Euclidean distance between each of these profiles and the other profiles of the group. In the k-means, this is not one of the original profiles. It is an average, because it is the point that minimizes the distance from each other. It is in general represented in this way in the books and so on. I have only 2 colors. If you have points here, I will not use the second color. I will say these are X. And you have this population, then you succeed. No. And then you see that this population can be represented by a point that is more or less in this position, and a point that is positioning there. So minimize the distance within. So we take just this and this in order to represent all the points, and these are these. In order to activate again the presentation, I need to slide. Good, thank you so much. There is always something good. Good. So this is the idea of this k-means. So this reduces, and we have chosen three centroid. They call them these points centroids. Why 3 and not 2 and not 5 and so on? We have done a little analysis, and we at the end the error, no, to consider just 3 instead of 5 and so on was limited and so on. So was a good way. There is an analysis, elbow method, and also, but these are the details. And this is quite common to use the k-means, no, in many topics. And obviously, the stochastic optimization is a little bit different with respect to the other, because it takes the same objective function as before, but for each scenario, we have also this element that is the probability of each scenario. So at the end of the scenario, you see also here in the, I think, the values here, and the scenario, for each scenario is included the probability. This is probability 1. There is only one scenario. These are 3. So the summation of the probability of these 3 scenarios is 1, but it is not the same, no? Because and so forth. So at the end we have many scenarios with different probabilities. So for each these scenarios there is a probability associated that is included in the objective function. So the objective function takes into account all the scenarios of the 3. So the group, the centroids, but each with their probability. Any questions so far? So we can also see the online optimization. When you have this decision tree, at each stage, during the day, the manager of the community can understand if it is in this scenario, I don't know, low production, low overproduction, and so on. So it takes these decisions, okay? But during the day happens something that is always. So instead of taking directly all the decisions for the next hours, so fixed by the day-ahead optimization, okay, we carry out a online optimization. So we are at the beginning of the stage, we do the optimization for all the stage again, and then implement just the first decision. So it is receding horizon, because after 15 minutes, so we discretize after 15 minutes, again we do the optimization for all the periods until the end of the stage. Why the end of the stage? Because at the end of the stage we have a different point in the tree of the decision. So we have in a different point. So we have a constraints that the operating values, in particular the level of the storage in the batteries, needs to be the same as the one calculated in the day-ahead optimization. And this is carried out for all the periods. So you see that there is a way in order to consider this. The calculation time of the day-ahead optimization is quite important. The calculation time in the online optimization needs to be very short, because after 15 minutes we need to do this. And this is facilitated by the fact that it is a deterministic optimization, and also the horizon is not 96 periods, but it is just the periods of the stage. And when you are going, no, it reduces, because it reduces, so it is always reduced. In general, we have 20 seconds and until 1 second at the end, because it is just on one period. So the characteristic of the online calculation, also the online calculation, it is the ADMM, so the iterative procedures that we mentioned, and we have implemented a parallel scheme in order to reduce the calculation time. The state of energy at the end of each stage, it is the operative condition in the battery. The there is the update of the expected profiles. So if you have also additional information or a better forecast of the PV load or also the load or the PV production during the day can be used in this framework. And there is also a Warren start calculation. We have seen that the greatest effort is the calculation of lambda. So instead of starting from a lambda that is just fictitious, we can start from the lambda that is calculated at the end. So this facilitates the things, so makes the thing. And I would like to show you the cases that case A is the 10 users, and you see here that there is the set of scenario in the intraday. And so we have generated several scenarios, not included in the initial set of scenarios. And for each scenario, you see different points. In the red are the dead solution. So for each scenario, we implement directly the decisions of the three calculated in the dead stochastic optimization. So since the scenarios are not exactly the same as those considered before, and also the centroids, we obtain this red solution. And then we calculated the intraday, and so you see that they are decreased. Okay? And then we do something else. We calculate also the so-called deterministic solution. So it is the deterministic solution that takes as known, perfectly known, the future. So it is the solution that is the best, because you know exactly what happens in the future. You see that with the intraday optimization, we reach practically the same objective function of the deterministic solution. So the solution that does not consider the uncertainty, knows exactly what is the behavior, the future behavior of the photovoltaic and of the load. This is also in case A, but also with this case. So there are here the loads, and you see practically the same behavior for almost all the scenarios. There are some scenarios in which we are a little bit in the middle. And also for a larger case, you see 83 bus in this network. And also here we have this effect that with the intraday, we can achieve an improvement, and very close to the deterministic solution. And so it is the last slide. So if you have some comments, I don't know, there are just the conclusions. We have seen the structure of the scheduling, the centralized procedure, the prices are the Lagrangian multipliers of the constraints. In the distributed procedure, the prices are updated at each iteration, but at the end, the results are very close. And then for each prosumer, the results confirm the cost reduction, and the three-generation procedure based on the key means clustering is adopted to deal with the problem of merging the stochastic information by using the obtained tree. Multiple decisions along the day are achieved, and the proposed multi-stage scheme for the scheduling provides in general improved results with respect to the corresponding forecast-based solution of the local energy community. This forecast is just considered just the forecast, and takes the decision and then implement during the day without updating. Any questions so far? The time is running. I do apologize. The basic of these optimizations are the solvers. And for this, all these calculations were carried out by using the solver that is Cplex. that is calculating also Gurobi obtain practically the same results. For my understanding, the same. so they are the same. So it is an optimization that it is based on these. So you can implement in different frameworks, GAMS, MATLAB, and so on. We have implemented by using this software that is called IMS. And also, but I'm not. It is not an advertisement. It is. I'm using the free version.
So, if there is no more questions, so we are ending this session number 6. So we'll meet in the second half just after the lunch. So we're having a lunch break now. So hopefully we can meet at 2:30. Right? Okay. Fine. So as last time is saying, so we are reducing the lunch break for 15 minutes, so it will be a 45 minutes of break. So we'll again meet at 2:15.
But you need to cut me.
No, you are in the flow. At guest house, huh?
You need to cut me. Say stop. Stop.